Welcome to a volume by shells example in X. So in this example, our job is to find the volume of the rotational solid formed by rotating the below shaded region about the y-axis. So again, we're rotating about the y-axis here. The region we are looking at is the region that is above the line y equals 1, under y equals e to the x, and to the left of x equals 1. So we're looking from x equals 0 to x equals 1, and from y equals 1 to y equals e to the x. So in this case here, if we draw our region, we have a mirror image of this little shape off to the left. And then we are going to rotate around. Essentially, we're looking at a cylinder minus a bowl, basically. So the shells we're working with are going to run from y equals 1 up to y equals e to the x. And then they will go out to x in terms of their radius. Shells are kind of hard to draw. It's actually might be easier to draw on the original graph. So we have a vertical line going from somewhere in our region, from the y equals 1 to y equals e to the x. We're going to basically sweep that around our y-axis and create a shell. So we're looking at a cylinder, which is just a vertical line through our set region rotated around the y-axis. And then we give it thickness dx. So our radius here is just r of x is equal to, that distance is x minus 0, otherwise known as x. Our height h of x, we are looking from y equals 1 to y equals e to the x. So this is from y equals 1 to y equals e to the x. So our height would just be h of x is e to the x minus 1. So we have, therefore, that our dv is 2 pi r of x. There's our circumference times h of x. That's essentially surface area of the side of the cylinder times our dx, thickness of our cylinder. So we are looking at dv as 2 pi x times e to the x minus 1 dx. Our bounds we are running from x equals 0 to x equals 1. So the region runs from x equals 0 to x equals 1. And so we are looking at our volume as the definite interval from 0 to 1 of 2 pi x times e to the x minus 1 dx. This integration is not so bad So we are looking at 2 pi times the integral from 0 to 1 of x e to the x minus x dx. X e to the x, we can run integration by parts on. So if we do our u dv, we said x is our u, e to the x dx is our dv. X would go to 1 and then 0. E to the x just stays e to the x. We add on the first diagonal, subtract on the second diagonal. We would technically add the integral of the end, but that's just an integral of 0. So we are looking at 2 pi times, we have an x e to the x minus e to the x. And then the integral of x is just, integral of minus x is minus 1/2 x squared. So the x e to the x minus e to the x came from my integration by parts. The minus x gave me that minus 1/2 x squared. Then we are evaluating this at 0 and 1. So this becomes 2 pi times, we have 1 e to the 1 minus e to the 1 minus 1/2 times 1 squared. And then we are subtracting off 0 minus e to the 0th minus 1/2 times 0 squared. Again, that 2 pi is multiplying everything. So this is 2 pi times, we have an e minus e cancels out, and we have a negative 1/2. Then we are subtracting off negative 1 minus 1/2. Sorry, we are subtracting off a negative 1. The rest goes to 0. And so this becomes 2 pi times negative 1/2 plus 1 is times just 1/2. And we get pi as our volume. Just a note, we could have done this using washers. But the inner radius would have been r of x equals natural log of x. And so our integral would have had a natural log squared involved. So our integral would have involved a natural log of x squared. And so I, in this case, just find shells to be easier. Sorry, it would have been a natural log of y squared. And it should have been r of y and a natural log of y. So for washers, for this case, we would have been using dy. Inverse of e to the x, we would have been looking at natural log of y. So we would have had natural log of y squared. Again, I find the shells easier in this case. Let me update my screen quickly. Again, it is largely a matter of personal preference, but I would prefer to work with an e to the x times x rather than work with a natural log of y squared. So that's why I prefer shells in this case. Right, in the next video, we will look at a shells involving dy. So that will be rotation around the x-axis.